With this lecture, we'll introduce some basic database concepts and terminology. And this introduction will then serve to be the foundation for the remainder of the course. A word of warning regarding terminology. In any area of specialization, there's bound to be a great deal of terminology, and in some cases, that terminology is very specialized or unique. The title we've given to this lecture is General Motivation. Let's consider why we chose that title. A database provides a way to organize, store, and access data in an efficient manner. Databases have, in fact, become a essential component to business operations, a sort of sine qua non. So in this lecture, we'll examine some of the factors that contributed to database becoming so important. Let's identify the objectives for this lecture, and there are actually quite a few. We'll begin by saying that we want you to build a foundation for understanding and working with a database system. We'll introduce key terms and definitions of database terminology, and as previously noted, there will be quite a few that we'll see. From a historical perspective, but also to provide a better understanding of the role that database plays and the need for database, we'll compare traditional file processing with the database approach, and this will include identifying advantages and disadvantages of the database approach. We'll explain the three schema architecture and why this is relevant to a database environment. We'll distinguish between operational, or what might be called transactional databases, and informational, or data warehouse or big data type of databases. These are two different approaches to data management, and they require an understanding of different methodologies that can be employed to design the database, but also to work with the database. And one other distinguishing characteristic would be the capacity or quantity of data that you would see within one approach versus the other. We'll explain the roles of individuals who design databases, those who implement them, those who use them, and those who are responsible for administering or maintaining them, database administrators. We'll tie this back to the three schema architecture. There are also additional objectives that we'll consider in this section, such as acquainting students with the broad spectrum of database applications and how organizations are using database applications for competitive advantage. We'll describe data models and how they are used to capture the nature of data and the relationships that exist among data. And finally, we'll describe the major components of the database environment and how these components interact with one another. So what is a database? A database could be thought of as an electronic filing system. It's an organized collection of logically related data. The operations that we would perform on a file folder or file folders within a filing cabinet are similar to the types of things we would do with a database. These operations include storing data for efficient retrieval. How do we accomplish that in a filing cabinet? We don't just throw the folder into wherever there's space, but the items are arranged in a logical order based upon some kind of encoding scheme, alphabetical, for example. And this allows for efficient retrieval of the data after it's been stored. We retrieve specific data. We don't always empty the filing cabinet, but we'll get one folder, and that folder pertains to the individual that is relevant to our immediate needs. We can also take a file folder and modify its content. Data that is no longer needed can be removed from the file cabinet, And the same idea of these operations that we're talking about with file folders in a filing cabinet can be applied to data stored within a database. Additionally, to protect the privacy of the data, we can lock the file cabinet. Well, we have security mechanisms as well that can be employed in the database to preserve the privacy and the integrity of the data. A database system provides the ability then to collect, organize, and manage data. Now, databases don't come in just one size, but they can be of various sizes and various complexities. Some of the systems that I've worked on have been rather small and simple, and others that I've worked on have been very complex and taken a long time to grasp the application domain in order to construct and design the database. So a simple database of contact information could be quite small in terms of the amount of storage required. And this is typically a personalized type of database intended for a single user or a small number of users. But large corporations have databases that consist of several megabytes, several millions of bytes, or gigabytes, billions of bytes, even terabytes or trillions of bytes. Such data might reside on a single mainframe computer or span multiple nodes on a distributed type of system. Such databases may be operational or transactional type of databases. What that means is because these things are going to be updated on an ongoing basis, there really must be efficient management of that storage. And this is where a background and understanding of data structures becomes important to understand how this vast amount of data can be managed and accessed efficiently. Very large decision support systems could be implemented as a data warehouse and could contain petabytes of data. Another question: what is a database management system? Well, a database management system, often abbreviated as DBMS, is a software system that enables the use of a database approach to both the storing and the managing of the data. The database approach to managing data overcomes the limitations of a file processing approach. The database approach begins with the proper design of the database, and this involves identifying entities, relationships, and attributes for this problem domain. A DBMS is a computer program, or more accurately, a collection of programs, which manages a database and acts as an interface between application programs and front-end tools which access the database. A front-end program communicates requests for data through the database management system. And a front-end program could be an interactive interface for executing database commands. This is something that is common to relational databases, what we might call ad hoc query tools. A user does not have to write an application program, they simply have to code a request in a special relational database language, which we'll talk about, called SQL. And this interactive tool allows the request to be entered and transmitted to the database for execution. When the results are returned from the database, they are then rendered on the screen through this front-end tool. An application program is another means of developing a front-end environment. So a front-end program that is an application program contains embedded database requests. These requests are also written in SQL for a relational database system. And that's going to be one of the selling points of relational database that we'll discuss a little bit later. Getting back to the distinction then between files and databases, there are numerous advantages of following the database approach. These include data independence, planned data redundancy, improved data consistency, enforcement of standards, and improved data quality. To continue with our response to what is a database management system, let's discuss the front-end tools. If we have an application program, this program might be written in a language such as C or Java or COBOL, depending upon the environment and the database system with which we're working. The interactive query tool, again, would be something that a user can sit down and start typing requests to the database in this language called SQL and getting responses. Note that the data entrusted to a database system will be stored in operating system files. The DBMS effectively serves as a barrier or a shield to the front end, preventing direct access to the files, or perhaps looking at it another way, preventing the need for direct access to the files. All requests are funneled through the database management system. So programs do not directly access the operating system files that contain the data. The requests go through the DBMS. With a relational database, commands inside a program and the commands issued through the interactive tools are similar. They are both written or constructed using this language called SQL. Although the operating system file services component is used to read and write the files that contain the data for the database, the organization and structure of the content of the files will likely be understood only by the database management system software. This is similar to the control codes that you would see inserted into a word processing document if you were to look at, say, a Microsoft Word document, but not with the benefit of using the MS Word program, but just open up the file itself. Such codes serve to indicate the font style, the size, and the appearance of text. The effect of the codes are seen by users of the document. However, the actual codes themselves are not seen by the user. So again, there's a similarity in terms of how we would expect the database files managed by the DBMS to be structured, what they might actually contain. They contain more than just the data. Relational database products include Oracle Database, MySQL, which is now the responsibility of Oracle Corporation as well, Microsoft SQL Server, Microsoft Access, IBM's DB2, and the list goes on. Databases used in businesses and organizations frequently have many people interacting with the system at the same time. This means that the DBMS has to take into account this multi-user environment. It has to provide security, preventing unauthorized access to data. Not every user is allowed to see every piece of data stored within a database. Integrity. The database system is modeled after some aspect of the real world, an application domain. There are business rules that must be enforced within our representation of the real world. Concurrency refers to the issue of multiple users attempting to access the same data in the same manner at the same time. Two people trying to read the same data, or two users trying to modify the same data at the same time. There has to be some guarantee as to how this will be conducted. That's concurrency control. Consistency refers to the idea of supporting transactions. In particular, go back to the integrity and the enforcement of business rules. What happens if a user is changing data? In the process of changing that data, the data may be temporarily non-compliant or non-consistent with respect to business rules. The system has to ensure that once the changes have been applied to the database, that all of the data conforms to the integrity constraints or business rules. And furthermore, with respect to the concurrency aspect, no other user should be able to see the database as it's in this state of change. Additionally, recovery is a responsibility of the DBMS. In the event that a transaction fails, or that the database itself fails, or a hard drive or whatever kind of media is being used to store the data, perhaps it gets corrupted and some of the data is lost. The system has to provide capabilities or mechanisms to recover from such types of failure. So why should we study database? Well, a database provides a way of achieving what we call data persistence. Data are not just manipulated within the working storage areas of some application program, but the data that is created or existing data that's modified has to survive the execution of the program. So persistence could also be achieved by simply using operating system files rather than using a database system. However, there are significant differences between the two approaches of using a file system versus a database system. We'll address a number of these in our examination of database. But first, what we want to do is consider what is it that we mean by data. Data can take different forms. We could classify data as structured, unstructured, or semi-structured. In general, data refers to stored representations of meaningful objects and events within the application domain. Structured data is represented in a strict format. Each record in a relational database table follows the same format as the other records in that table. Structured data is often numeric, textual, or of a date-time variety. Unstructured data has a very limited indication of the type of the data. This applies to images, videos, and documents which may have embedded data. In general, multimedia would fall into this category. With semi-structured data, schema information is mixed with the data values. And this is because each data object can have different attributes that are not known in advance. Thus, this is sometimes referred to as self-describing data. XML, the extensible markup language, was initially designed as a way of adding markup information to text documents, but now it's become an important language because of its applications in data exchange. Data by itself is generally not very useful. It is only after the data has been processed, summarized, and organized that it becomes useful for decision makers and knowledge workers. We make a distinction here between data and information. Processed data becomes information, and this can often be made available to users in the form of reports or graphical displays. Business intelligence, or BI, is the process of obtaining information about a business or organization from available data. Business intelligence enables answering business questions to allow decision makers to respond quickly to changes in the business. Business intelligence begins with day-to-day information required to operate the business. For example, it might be necessary to know what was ordered yesterday and what was shipped. Which accounts are more than 30 days outstanding? Information comes from data collected during business transactions in an operational data store. With an operational data store, also called a transactional database, the database content or database state is subject to frequent change. New data will be added. Existing data might be changed. Still, other data may be removed from the database, all to reflect business activity. Many BI questions require access to historical data or data from different sources. Because of this, business intelligence systems often are built upon a data warehouse, rather than a transactional database. The historical nature of data in a warehouse is used to accomplish time-based analysis or trend analysis. Such data stores separate the analysis workload from the transaction workload and enable an organization to consolidate data from several sources. So very often, an organization has an operational data store for daily operations and accumulate data from such data stores into a decision support system, a data warehouse, where the data can be analyzed. The nature of the questions answered through BI might be more general than simply identifying single facts. Common questions include, how is my business performing? What factors are influencing my business? Where is my business headed? Where should we focus our efforts? To answer questions of this sort requires an understanding of the strategic goals of the organization and which areas of the business are performing well. The report shown here indicates several types of data entities. Consider the objects or entities that are reflected in this report. We have courses and sections of these courses or classes. We also have students enrolled in a section. The data that describes a course includes course number and sponsoring department, as well as a course name. The data that describes the scheduled class or section includes a section number, a semester, and a year. Thus, we've gone from just raw data to some type of useful information by organizing the data. We have a course, CSC 341, which has a name. We have a scheduled offering or class, Section 1, offered during the fall semester of 2020. We have student data. The different entities are related. This is the idea of a database. It's important to distinguish between the description of the database and the database itself. The description of a database is called the database schema. The database schema information refers to the names of the attributes, relationships, and classes or object types, essentially the description of the data. The distinction between the schema and the state of the database is also very important. When we define a new database, we specify its structure or schema. And that's all that we specify. The corresponding database state at that initial point is empty. We have no data. We obtain the initial state of the database when the database is first populated or loaded. Although the schema is not supposed to change frequently, it is not uncommon that changes occasionally need to be applied to the schema as requirements within the application or application domain change. This is referred to as schema evolution. Another important term or concept is metadata. Defining a database involves specifying the data types, the structures, and the constraints of the data to be stored within the database. The database definition or descriptive information must also be preserved in some way. It will be stored within the DBMS. It takes the form of what is sometimes called a database catalog. This data is referred to as metadata. It's data that describes the properties and the context of other data. Metadata gives a self-describing nature to a database system because we're not only storing the data, but we're storing descriptions of the data the data types, the structures, names of the tables, names of the columns, and so forth. A general-purpose database management system is not written for a specific database application. It must make use of metadata in order to determine the structure of files in a specific database. Thus, metadata really pertains to the underlying structure of the data. When you design a database, you are specifying its metadata. When you populate the database, you are putting data into the database. So metadata includes descriptions of the properties or characteristics of the data, including data types, field sizes, allowable values, and data context. This is the information that we gather as we're designing a database. Files and databases provide a way to store persistent data, but there are some important differences between these two approaches. Prior to the advent of databases, data was stored in individual files, each being used by a separate program. This was the traditional file processing approach to data storage. As business applications became more complex, it became evident that traditional file processing systems had a number of shortcomings and limitations. Database systems were developed to overcome these shortcomings. However, there's still a lot of data that we see stored in traditional file systems. Legacy systems still abound with traditional files. Even Excel spreadsheets, which are relatively modern, would fall within the same category as file systems. Many companies store their important data in a myriad of spreadsheets, and as their businesses become more complex, they run up against the limitations of these storage methods. Simple operating system files are common to spreadsheets, word processors, and other productivity software. Simple operating system files can also be used to store application data in separate files for employees, departments, vehicles, parts, policies, and so on. The organization of such files is based on a record, which is a simple collection of data items. Thus, a file is a collection of data items. So what's a database? A database is a collection of data items as well, but the database also captures relationships between data items. This is a collection of logically related data. So there are two common approaches to data persistence: use simple operating system files or use a database. Different models of database, such as the network model, hierarchic model, relational model, object-oriented model, represent the relationships in different ways, but they all capture relationships. These models differ in how the data would be stored, organized, and accessed. Here we have a policy master file and a claim file for insurance policy information. How is the claim file related to a particular policy? If you examine the content and structure of the records in the claim file, what is it that tells you a particular claim applies to some particular policy? You may be able to make a guess based upon the name that we assign to a field. However, there is no formal association between the records in these two files. The logic of an application may reveal an association, but it requires reading and comprehending the code of the application. Furthermore, if you want to write a new program to manipulate the claim file, nothing would prevent you from putting bad data into this file. That is, claim information that doesn't relate to an existing policy. When policy and claim are defined to a database system, the relationship is also defined. It's made explicit, and it's recorded within the system. Because the system stores information about the relationship, the system, not simply an application program, can enforce the relationship. This is the notion of data integrity. See, the relationship is recorded as metadata stored in the system catalog. Knowledge of this relationship is used by the system when data are accessed or manipulated. In a general sense, a database is a collection of related data and has the following implicit properties. The database represents some aspect of the real world. The database consists of a logically coherent collection of data with some inherent meaning. The database is designed for a specific purpose, an intended group of users with some preconceived applications. Databases come in different sizes and complexity depending on the application domain. The DBMS software must work equally well with any number of database applications, as long as the database definition is stored in the catalog. In traditional file processing, data definition is typically part of the application programs. Well, there's a lot of material to be covered. If you review the objectives that we introduced at the start of this video, you'll see that we've not yet come close to finishing everything we wanted to cover for this lecture. So I think it's a good point at which to take a break, kind of stretch a little bit, absorb what we've thrown at you at this time, and then we'll come back and pick up where we left off. So in our next video, we'll continue our examination of the general motivation for database. See you then.